I would like to explain the brachistochrone problem in just 10 minutes. The presentation is based on this textbook, Modern Classical Mechanics. You can have, this is just a very brief introduction. It is the brachistochrone problem is about finding the curve. Along this curve, a particle will slide in the shortest time. As we could see, this black particle is always sliding and reaching the points faster than all the other particles that are moving along the straight lines. The historical perspective for this problem may be somehow important. The story starts at the afternoon of January 29th when Sir Isaac Newton received a letter from the Swiss mathematician Juan Bernoulli. This letter contained an unsolved, it was a challenge in fact, an unsolved brachistochrone problem that was published about 6 months ago. The challenge has gone forth to mathematicians to solve the problem. It was a challenge and they were given a time limit of 6 months. In fact, the problem was already solved by Leibniz, the German mathematician, and the arch-rival of Newton, because both of them are recognized as the original inventors of calculus. Leibniz already solved the problem but asked for the deadline to be extended because Newton did not receive yet the letter. Bernoulli agreed and sent the problem to Newton to stump him, and showing that he did not really understand the calculus as well as the continental mathematicians in France and Switzerland are able to understand. Once Newton has received the letter in a testimony by his niece, he did not sleep until he solved it 4 a.m. in the morning, and then Newton sent the solution at the same morning to the Royal Society so that it would be published anonymously. Okay. However, Bernoulli didn't doubt that when he saw the solution, he was sure that this was the work of Newton, and he said that from the close of the line, we are able to understand or identify that this is the work of Isaac Newton. Okay, the problem was also solved by another two mathematicians, Bernoulli's older brother and the French mathematician L'Hopital. The mathematical, now we, after having this background, we are ready to present the mathematical formulation of the brachistochrone problem. Given 2 points A and B that are located in a vertical plane, we need to find the shape of the curve connecting A and B, such that if there is a bead sliding or if there is another object that is following this path and sliding along this path under the effect of gravity only, without friction, okay, starting from rest from A and reaching B, we need to find the curve such that the time will be minimum. This is the problem. And there is a spoiler now that the solution of the problem is not the straight line. The straight line is not the path that will get us the lowest or the minimum time. It's different. The straight line is not the solution. So to solve this problem, we need to work using the Euler-Lagrange equation. First of all, we need to describe the motion. The motion is frictionless, hence we can use the principle of conservation of energy, or that the kinetic energy plus the potential energy is equal to a constant. The kinetic energy is half mv squared and the potential energy is equal to mgh. Please remember that h must be positive upwards, and since we are selecting y-axis to be directed downwards, then y is simply equal to negative h, or h is equal to negative y. That's why the potential energy will be equal to negative mgy. Remember that the coordinates of the endpoint xb, yb should be given, and we are assigning a here to the origin. The start will be from the origin and the end will be xb, yb. Since we have written the kinetic energy and the potential energy, we can sum them together and assign them to a constant. However, this constant can be simply equal to 0 because at point A or at point A capital, we know that we are starting from rest and it is located at the origin, hence the velocity is equal to 0 and due to rest, and y and h are equal to 0, so hence the potential and the kinetic energy are 0 and the constant is 0. That's why we know the constant. Now we return back, or we can rewrite the equation as half mv squared minus mgy equal to 0, and the mass of the particle can be cancelled out. We get half v squared equal to gy because this can be transported or transferred to the right hand side, and then we multiply by 2 and get the square root, hence we get that v is equal to square root 2 gy. From elementary mechanics, we know that v is equal to ds by dt, where ds is an infinitesimal line element whose length is equal to square root dx squared plus dy squared. Suppose that you are focusing on two infinitesimally close together 2 points. The distance between these 2 points will be equal to the square root of the horizontal separation, which is dx, and the vertical separation, which is dy, which is square root dx squared plus dy squared using Pythagorean theorem. Hence, v, which is equal to square root 2 gy, is equal to ds by dt, can be written with this expression. Since we are interested in the curve of the minimal time, hence we calculate the time to be the integration of dt from point A to point B. Hence, the idea now is that we need to write this integrand in a way that is familiar to anyone using calculus of variation. To do that, we need to select an independent variable and a dependent variable. From experience, we will set x to be the dependent variable and y will be the independent variable. To do that, we will have to take dy outside the square root. Hence, we will have dx by dy the whole squared plus 1 over root 2 gy. Dx by dy is simply x prime. So the integral will be written as the square root of 1 plus x prime squared over square root 2 gy. Again, x is selected to be the dependent and y is independent, and this choice is just guided by the experience. So we can now use this Euler-Lagrange equation, partial f by partial x minus d by dy, which is the total derivative of partial f partial x prime equal to 0. Now we are ready to solve the problem using maxima. First of all, we state that x is a function in y, and for some technical reasons or few mathematical reasons, we need to tell maxima that sine theta is greater than 0. This is the integrand that we have already derived in this slide, 1 plus x prime squared over square root 2 gy. You can observe that partial f by partial x is equal to 0, and since we are applying Euler-Lagrange equation, hence d by dy of partial f partial x prime is equal to 0. Hence partial f by partial x prime is equal to a constant k, as we can see here. This is an integration constant. Now, for technical reasons related to maxima, I had to square both sides of this equation to derive that partial x, or sorry, dx by dy is equal to this expression. I will just use the positive root or the positive solution, and I will assign a small, which is another constant, equal to 1 over g2k squared. Again, this is an integration constant instead of using the k. So the equation can be written in this way, and it could be simplified to be written as we could see here. Now we can integrate this, but however, and even maxima can integrate this expression. However, to get a curve that we are familiar or a solution that can be interpreted, we will use the substitution y is equal to a over 2 multiply 1 minus cosine theta. This is the result of the substitution, and we will focus on the integrand to explain something. Okay, when we focus on the integrand, we multiply the denominator and the numerator by square root of 1 minus cosine theta, so that we could get this expression. Square root of 1 minus cosine squared theta is equal to sine theta. Hence, sine theta will be eliminated or cancelled out from the numerator and the denominator, and we will get this somehow simple expression which can be integrated easily with respect to theta to get this result. So x is equal to a over 2 theta minus a over 2 sine theta, and this is why. This is the equation of a cycloid curve. I will explain shortly what is the cycloid curve. However, please note that I did not introduce here in this integrand, I did not introduce here a constant of integration because we need to satisfy that at x equal to 0, y we should be equal to 0. By the way, this is the equation that we have used in the substitution in the integration. If we substitute by 0, we'll get cosine 0 equal to 1, 1 minus 1 is equal to 0. So y is 0, also 0 minus sine 0, which is a 0, we get satisfaction of the initial condition. So we didn't introduce a second integration constant. And given xb and yb, we will be able, and this should be given because we started by assuming that we know the starting and the end points. Using xb and yb, we should be able to calculate the constant a and the final angle theta. So what is about this cycloid curve? As you could see, this cycloid curve is the curve that is traced by a point, a fixed point on a cylinder that is rolling. Again, I am trying to, this is like getting a screenshot of the solution. This is the fixed point and this is the cylinder that is keeps on rolling, as we could see. The distance of a rolling cylinder, the distance covered or the distance traced by, not by the point but by the center of the cylinder is equal to r times theta. And this animation here explain this. Suppose that you are rolling this cylinder for a complete revolution. Okay, suppose this is a tape that is being rolled. The length of the tape that has been unrolled is equal to the circumference. The circumference is equal to 2 pi r in fact. So 2 pi is the angle that is rotated by this rolling cylinder, and hence if we do not have a complete revolution, if we just make a part of a revolution, the distance traveled by the center will be just equal to r times theta, where theta should be in radians. Now let us examine the equations for x and for y. This is the point that we are trying to trace the position of this point. We see here that the full distance traveled by the center, as we have already mentioned, is r multiplied theta. However, this point is located at the left, so we need to subtract this distance. This distance is equal to r sine theta. This distance from trigonometry is equal to r sine theta. That is why x is equal to a over 2. A, by the way, a over 2 is the radius. So the radius multiplied by theta will get us the distance from A to B. However, we need to subtract this distance, which is equal to r sine theta. So this is the x. For the y, the vertical location, we can add the radius r, or a over 2, and we need to add this distance. This distance here is equal to negative r cosine theta. The negative sign is present because here theta is obtuse, and the cosine of an obtuse angle is negative. So negative multiply negative, we get a positive, hence we are just adding. This confusion occurred because theta here is obtuse. You should pause the video and think about the case when theta is acute. Finally, this is an experiment to illustrate what should happen or whether the curve of the fastest descent is the cycloid. As we could see for this slow motion video, we can see here that the curve, we are having here a straight line, and we are also having the cycloid and even another curve. The cycloid curve in the middle gets us the shortest distance. Thank you very much.